Hello everyone, in this video I'll be explaining the 10th program of Data Structure Laboratory, that is about design, develop and implement a menu driven program in C for the following operations on binary search tree of integers. So first of all, let us see what is binary search tree of integers, how to construct any binary search tree of integers. As the name suggests, binary search tree, so in that you know that binary search concept is based on finding the number, middle number, and the left of it would be the left of that middle number would be the lesser numbers than the middle number, and the right of it would be the higher numbers than the middle number. So even a binary search tree is based on that concept, For example, if I consider a simple example, like, let's take a value. The values what I'm going to here consider are simple one: 6, 9, 5, 2 and 8. Okay. So here I am going to consider only these set of values: 6, 9, 5, 2, 8 and 8. So there are 6 elements. Let's see how to construct a binary search tree for this. So let's start with this number 6. So you need to create a node for it, and after that let's try to add the next number. Where do I add? So as I said earlier, like a binary search concept, here also 9 has to go to the right of it, as the 9 is bigger than the 6 value. So it has to go to the right of it. It has to become a right child of a 6. Then I have to take the next element. This is done. Next element is 5. Where do I add? As let's start from the root of the tree 6. So let's compare 5 with 6. What happens? 5 is lesser than that. So what you do? You have to make it as a right child. Then I will try to add next element, that is 2. Let's again start from the root. Always you need to start from the root of the tree. Try comparing that 2. What about 2? 2 says that it is less than 6. So you have to take the branch of the left child. Again, after comparing with this, you have to compare with this, because as the binary search tree, we cannot add one more child to the same node 6, because the maximum number of child can have here is 2, not more than that. So 6 I compared, no, not possible. So you come down, compare with the 2, so it is lesser, so it becomes a left child of a 2. Okay, left child of a 2. Now when it comes to 8, where do I add it? I will add it to I will compare first with this. I will compare 8 with 6. Obviously it's bigger, so I will come down. 9 is less than 8, isn't it? Less than 8. So I will add it here. Now we have one more value. Okay, that is 8. Where do I add it? I will start with this. 8 I will compare with 6. No. 9 I will compare 6 with 8. It is lesser, so I will compare here 8 with 8. So what happens here? It is same. When it comes to this, you have to verify whether the left child or whether the left child is free. If the left child is free, you can add it as a left child. That is the arrangement we do it for a duplicate elements. Okay, suppose if the left child is not free for 8, then what you have to do? You can make it as a right child. Okay, so this is how I construct a small binary search tree. Now let us try creating the binary search tree, and then we'll traverse the BST in order, pre-order and post-order. Okay, so you all know the binary search tree order for Inorder, isn't it? That is vertex, left and right. When it comes to preorder, vertex is first you have to visit, and then left child and the right. Okay. Next, when it comes to the post order, elect, right, and finally the vertex. So this is the method you need to follow. So if you do not know the traversal of a Inorder, preorder and post order, first learn that, and then you can understand this program explanation. Okay. So let me start the program explanation. First of all, I have to include stdio.h. After that, I have to include stdlib.h. Okay, these are the necessary header files for this program. And next, since this particular node of a tree, okay, node of a tree contains mainly the integer elements, data element, isn't it? So mainly what it will have, suppose if I take node 6, isn't it? So what each node is going to contain? Node is going to contain the that is three things. One, it's a data, and it will have a link to a left child and right child. So that's why I will put this value information in the structure, and the name of the structure is tree node. Okay, name of the structure is tree node. After that, data, that is 6 or 5, whatever way element integer you're going to give. Next, once that is done, next is what? Next is, as I said, left child or right child of that. So struct tree node star left star right. So the star left is going to have the link of the left child, and right is going to have the link of the right child. Next, next we have to, I will initialize the root. Okay, and the name what I am going to give is, because every time you need to start the tree, what is that, the traversal from the root node, okay, of a tree. So that's why, so first you need to do this. Okay, that is, you need to initialize star root as null, because initially it is empty. Okay, you have to define that, you have to initialize that. After that, let us start creating the binary search tree. So let me take again the simple example 69528 for the construction. Let us understand the function. So function name for creating a binary search tree is create node, and what I am supplying to this, that is the data value, that is one after the other. These values I am going to give, and at the end, after the construction of the each or after the insertion of the each node, okay, or after the insertion of the each element into the tree, you're going to return the address of it. Okay, you're going to return the address here. So now I'm going to create one new node. Okay, so that is first time I will create one new node. Name node is what? That is for 6. First I will create. Okay, this is a new node. So I will create a what is the structure for new node. After that, I will allocate a memory for it. That is using a malloc function. Okay, for this node I am going to allocate a memory, and then I will add the data in the data field. In the data field, what I will add? The value, that is 6, and then the left child of it and right child of it is, right now it is null. It is null. So initially it is null, and then now I am going to return the address of that. So return new node. Okay, when I call the next time the create node, create node, what it is going to do? It is again create a nodes like this. That is, for the insertion, it is going to create a node. So one more time, it is going to create a node like this 9, and this value will be null, and this left child and right child will be null. That is what done by the create node. Okay, and once after creating this node, it is going to return the address of it. Suppose if it's 100, 200 is the address. Suppose if it is 200 is address of this node, that it is going to return. Next, we'll see how every time you create a node, how you are going to insert into the binary search tree. That insertion actually you are doing here in this portion. So kindly correct it. If you have got confused with this explanation, this is just for creating the node. Okay, just for creating the node for each integers. Okay, now you have to insert what these node, insert these node with their data. Okay, let us see now the insertion into the binary search tree. Now I have a values 6, 9, 5, 2, 8. What I will do? Let's assume that I'm going to let's see that how to construct a binary search tree now. So that is accomplished in the insertion function. Okay. So insertion function, first of all, it is going to check that is the first node I'm going to construct. So that's why I'm checking here in this particular statement whether star node is equal to null. Yes, star node in the sense whether the root is right now it is null. Okay, if it is so, that means it is empty right now. Binary search tree is empty. If it is so, you create a node for a data. What you are going to? You are going to create one first node. Okay, 6, and after that, else if the next time when you call a insertion function, what happens? The second when you are entering the second element, what happens? It is going to check whether the data is less than the star node data. Star node is going to point to this. Yes, no, it is greater. If it is greater, what happens? You insert to the node right this data. Whatever created node for 9, that you're going to insert here. Okay, and the next time when you call a insertion function, so here when you call a insert a function after this for the next element 5, what happens? So you'll first compare, so your node, okay, and the data will be sent. Data this time is 5. When it is sent, what happens? It is going to check whether it is node equal. No, it's not. Then it is going to check that whether node data, that is whatever you are sending, is less than the node data. Yes, node data is 6, right? It is this element data whatever is sending is less than. If so, insert to the as the left child. Insert this as the left child. Okay. Similarly, when you call again insertion function for 2, what it is going to do? So if you when you send 2, okay, you will have the root node address of the tree. So you start again from this time whether a node is equal to null. No. Whether the data is less than the node data. Yes. If so, what you are going to do? Insertion node left data, but node left is right now it's not empty. So again it is going to call this whether the node is equal to null. No, right? Node is not equal to null. In that case, what you are going to do? uh, so for this you're going to check whether the data 2, whether it is less than the node data. Yes, it's so. Insertion node left data. Insertion node left data, that is you call again, and here what happens, you will come to know that node left is null. Add it to this as a left child. So that is what it is told here. Okay, so let me take one more example, that is 8. So again you will have the root address. Node will have the root address. This time you want to enter which element data into the as a node into the tree, that is 8. Okay, so you compare whether the node is equal to null. No. If so, whether the data 8, whether it is lesser or greater, it is greater. So that means you are going to this line. You can observe here this line, data is greater than the node data. If so, what you are going to do, insertion node right, insertion node right, but the node right is not null, isn't it? Insertion node right, this node's address will be sent. Okay, this, suppose this node's address is 100, that will be sent this time. Then again whether it is going to check that whether the node is equal to null. No. If so, it is going to check that whether the data is lesser than the node data. Data is lesser than the node. Yes. If so, insertion node left. Insertion node left is what? That is, node left is this. Its portion is right now null. If so, null and data will be sent. Null and data will be sent. So here this time null and data that is 8, that will be sent. So it is node is equal to null. Yes. So what you do? You create a node. You create a node to here itself. Okay, as a left child. That's what we got, isn't it? As a left child, you have to add it. So this is about the insertion. And remember, suppose any time if you get the data that is equal to node data, that is if you get a duplicate element, in that case what to do? So I have already explained previously in the beginning how to insert the data if there are duplicate elements. If there are duplicate elements, go to the appropriate position, correct position for a duplicate element. After that, if a left child is empty, then what? This is not comment need to be removed. Okay, so if the left child is empty, add it as a left child. Okay, add that data as the left child. If a left child is not empty, then add that data as the right child. That you need to remember. Okay, that is what the arrangement we made for a duplicate elements here in this program. Okay, let me tell you again about the duplicate elements. So whenever you come to know that there are duplicate elements like this, for example, if I have 6, 9, 5 and then 5. Okay, 6, let's take another 6, 5 and then 6. So 6, first you will add here 5. Now you have 6, which is a duplicate element. Where do you add? So you can't add it as a left child, as the left child is filled, place is filled. So let's add it as a right child, because the right child is vacant. So that is what we are going to do here. If suppose node left is null, then insert this particular data as the left child, otherwise right child. That is the arrangement we have made here for the duplicate elements. Okay. Now find element in the in the tree. That is, we are going to search for an element in the tree. Okay, if suppose the tree is like this, 6, 5 and 9. Okay, let me take a simple tree. Let's take 2 here. Okay, so this is a tree I'm going to consider. If this is a tree and you will have a root node address, suppose this root node is 100, so its address will be given. So let's name this as root. Okay, that's a root node. And the data what you are searching, I want to search for 2. Then what happens? Whether node is equal to null? No, it's not empty. That is, root is not null. In that case, what you're going to do? In that case, you're going to check that whether data is less than the node data. Whether the data is less than the node data? Yes. Okay, data whatever supplied is less than the node data. If so, what you're going to find element in the left child. So node left data. Then again this time root is, suppose this is 100. So earlier it was 100, this was 2. Let's assume this node address is 200. So now the 200 will be sent along with the data. So this time again it is going to check that whether the data whatever sent is 2, whether it is less than the node data. Node data is this node is 200 node. So its data is 5. Whether it is lesser? Yes, 2 is less than 4. So in that case, what you find element in the node left? Node left is 300. And the data you're going to send is 2. So this time again it is going to call the find element function, and these data will be replaced. Okay, 302. So what happens this time? 302. So here now we got the node isn't it? So node whatever you have got, the data, whether it is less than? No. Node data is also 2, isn't it? And the data what you have supplied is also 2. So it is not less than, it is not greater than, then it is going to else part. What is that? It's going to tell you that data is found. What's the node data? That is 2. Okay, this information is given or displayed on the screen. Okay, so this is about the find element, searching the element in the tree. Next we'll see the next one, that is Inorder, Preorder and Postorder traversal. What is Inorder, Preorder, Postorder traversal? Already in the beginning I have told what it is going to do, isn't it? So here first of all, let me take a simple one, 2, 1 and 3. So what's the Inorder traversal of this? Because we know that it is vertex left and right. So vertex, that means the root of this particular thing should come in the middle. So 1, 2, 3. That is what the answer you are supposed to get for the simple one. So node here, first of all, the root node's address will be sent. Suppose the root node says 100, that address will be sent. 100 whether it is equal to null or not equal to null. So what do you mean by equal to? If the root is null, so if the root is null, that means it is empty. So root here is not null means what? There exists a binary search tree. Yes, of course there exists a binary search tree. That is what the meaning of node not equal to null. In that case, Inorder node left. Inorder node left. What is Inorder? Inorder node left. So its nodes left is this node's address, that is 200. Let's assume this node's address is 200. So in order of 200. So again it in turn calls this Okay, so interns calls this. So in that case, what happens? Node is not equal to null. So this particular node is not equal to null. That means there exists a node. So in order node left. In order node left, when you're trying to call, it is going to, there is no node left for this particular node. It is going to send what? Null. So in this time, what happens? Node is, so this particular line is going to get null. So null means what? Directly this particular line is going to its execution finishes, and then it is going to print node data right now where it is at this place. So it is going to print this node data, that is 1 it is going to print. Then what happens? Inorder node write. What is inorder node write? There is no write node for this. Okay. So once there is no node write for this, then what happens? So first of all, so let's remember, we started from where? We started from the node 100. Then we came to 200. Then we came to node 200, isn't it? The node which is having address 200 we came. So we finished at this place. Since it is a recursion, we finished at this place. Then that means again we need to go back to 100. Okay. So that means we finish the left portion of this particular part of this particular binary search tree. Then what it is going to supposed to print? It is print node data, where it has come right now. Finish this portion and now it has come back to this portion. So it is 2 it is going to print. After that, finally it is going to take a in order on node write. Node write is what? 300. So this time it is going to send 300. Obviously it is not equal to null. So in order node left is null. So it is coming back to this particular place, that is 300. Then its value is printed, and after that it's going to check node write. Node write is also null. So it has finished this. It has touched all the nodes of the tree. So hence it returns from the inorder by printing these values. Okay, by printing these values. Let us take the same example for the next, so that this particular execution is more clear. Okay, I mean the working of this particular code is more clear to you. First of all, I'm going to, when I call a preorder, what it is going to, what it needs, it needs a root of the root address. Root of, let's assume, so let me write this in the form of this way: 2 node left, node right. So this is how actually it is going to, okay. So this is how it is. So this portion is null, this portion is null, this portion is null. Now, when I call a preorder function, how exactly it is going to work? As I told earlier, first of all, you need to send root address. So let us assume the address for this is 100, this is 200, and this is 300. Okay, for this particular node. Okay, and remember, each node will have its left and right. So left, this particular node, that is node address 100, its left link is pointing, this left link is pointing to 200, and its right link is pointing to 300. Whereas this node's left link is pointing to null, right link also pointing to null. So here also this node's left link and right link is not pointing to null. That means it is not having any child. So now, as usual, I will pass 100. Right now I am going to see a preorder traversal for this node. Okay, real traversal for this particular binary search tree. So node is not equal to null. That means there exists a binary search tree. It's so what I'm going to, so first time I called preorder of 100. Okay, next tile node is not equal to null. So node data. What is node data? Node data is right now it is at 100. So that data I am going to print. What's the data? That is 2. Next, no preorder node left. What is node left? Node is right now 100, node left is 200. So let me finish execution for this portion. Okay, remember preorder hundreds. When I call preorder 100, I just printed this line. Then I called this line. Okay, after that I did not finish executing this particular line for preorder 100. Still its line is pending. So in between I came, because of this line I jumped to preorder 200. So preorder 200. So here in this last line execution is pending. Remember that. So preorder 200, when I call node is not equal to null. That means there exists at least a node or a binary search tree. Okay, or a subtree, I can tell. At least a node or a subtree exists. So node is not equal to null. So print node data. Print node data in the sense right now we are at address 200. So its data is 1. So I am going to print. After that preorder node left. What is preorder node left? Preorder node left is null. Preorder null. Call preorder null. So if since you have called preorder null, what happens? Its execution terminates immediately, because this particular code will work only if node not equal to null. So this particular line will terminate immediately. So this particular line will terminate. Then comes to preorder node write. Node is right now 200. Preorder node write is again preorder null. Null. As I told, null means this particular code, even if you call a preorder null, it is going to terminate immediately, because these portions of the code will execute only if there exists a node or a subtree. So that means in that case this also terminates. So again this terminate, this again you will come to where, so 200 also you finished. Okay, for this particular portion of the program is finished. Then we have a last thing, that is preorder node write. So this code is done. Again see, from here you have jumped to here. So this was done actually. So from here directly you jump to here. That is its code part is done. So directly you will jump to preorder 100. So in that case what happens? Preorder 100, in the sense, in the preorder 100 only last line was pending. That is what I had written here. Last line was pending. So this, so node 100's write. What is 300? Preorder 300. So this time, that is the last line you are executing, that is preorder 300. So let me tell. So after that its execution will be over. For preorder 100, its execution will be done. Okay, that's why I'll change this from preorder 300, how it is going to start its work. Let's see that. Now, so when it is preorder 300, so node is, there exists a node at least. Node data. What is node data? Node is right now is 300. 300's data is 3. So let me print that. After that preorder node left. Preorder node left is null. And so that means that is immediately terminates. Preorder's node write is also null, so it terminates immediately. So its execution will be over. So this is how it is going to print the pre-order traversal. Next we'll see the last traversal, that is post order. That is post order. How the same program is going to give you the answer. Okay. Post order, as usual, I am going to start from the root of the tree. Root of the tree is 100. Root of the tree is 100. Then node is not equal to null. Yeah, that means node exists. Post order node left. What is post order node left? Node left is 200. So you are going to call, first you called, let me write in the form of stack. First you called post order 100, correct? After that you are calling now post order 200. So you're calling node left. Node left means what? 200 now. So you again calling. So this transition control again it goes to here as soon as you call. After that this is getting now changed. So I have put that in the stack form. So that you can easily understand if you have not understood the previous explanation. So all these things are similar. Okay, this kind of explanation, that is stack usage, is similar in all like in even in case of previous one. If you feel that this way you can understand, you can try analyzing the previous two traversals. Post order 200. So in that case node is not equal to null. Yes. So again post order node left. What is post order node left? This time it is 200. Node left this time is null. So this post order null it is going to call. Node left is null. So but node left it immediately returns. That means this person's or this particular task is vanished immediately, because as there is no task to perform. Then post order node write. So that means again you have come to the control of 200. What's the node write for a 200? That is again null. So again you call post order null. Again you call post order null. Okay, as soon as you call post order null, what happens? It is going to return the control immediately, as there is no node exists. Return means even from the stack its content will be, this particular content will be written. So post order node write is done. Then this particular thing, node data. What is node data? 1 node, because right now you are under the control of which node? That is 200. So I am going to print now node data 1. This one will be printed. After that, see, you can observe for post order 200, this line is also done. Finally you will return. As soon as you return, all lines of for post order is done. So you will come out of it. Right now you are under the control of post order 100. Post order 100. So you know that post order, you just finished post order node left for 100. Okay. So I had shown here, you can observe. So then next you will come to post order node write. So post order node write. You're at which line? This line. Now you are in this line now. Line 2. Post order node write is post order. What is the node according to 100? 100, that is 300. So again, now this will be 300 and this, okay, this will be 300. Because of this it is 300 you are calling. So whether the 300 node is does not exist? No, it exists. So in that case again you are calling post order node left. Post order node left. So since you are passing the address value 300, its left is null. Node 300, node address 300, left child is null. So that's why this will terminate immediately. That means you will come to here. Node right is also for that null. So then what happens? Post order node right is also null. So that also terminates immediately. So directly we will come to the third line. Okay. So you're printing what this time? That is 3. You're printing 3, and that means for post order 300 you have finished all these lines. So that means, and you are returning means this particular content will also vanish from the stack. Okay. Next, as soon as you return, next what happens? Next again you will come under the control of post order 100. So you know that this line is done, this line is done. Which line is remaining for post order 100? That is the last line, this line. So node data. What is node data? Under the control of address 100, that is 2. This particular data. So I am printing now 2. So you can observe here left, right and vertex. That is the rule of post order. Okay. So this is how actually even in order, post order, pre-order works for even a bigger tree. Next is finally incorporate all the functions what we have written in the main program. Just you have to add those functions into the main program. Let us see what your main contains. Main contains the data and the choice. So choices, out of the menu you need to select the choices, and the choices or a menu are written under the while loop, written under the infinite loop. Okay, that is infinite loop you have written using, or you have constructed using while loop. Okay. Next, next you have these printf statements are for menu construction. Once the menu displays the creation, search and in order, pre-order and the post order traversal. Okay, menu will display all this. Then it will ask you to enter your choice. Enter your choice, either 1 or 2, or what is that, 1, 2, 3, 4, 5, 6. 6 choices. 6 is for exit. So out of this you can select any one. Okay. So as soon as you give a choice, scanf will read that through keyboard, and then if you select one, it is going to, for the that is, if you select one, it is going to read the case 1 part. Let us see what is there in the case 1. In the case 1 you can that is for creation uh, of a binary search tree. Okay, you're going to read the data values whatever you want to enter, and then you're going to insert the root address and the data. You're going to insert the root address and data, and remember, root address is initially none. Okay, that says that the binary search tree right now it is empty. That means you are going to yet to construct the binary search tree. That's the meaning of that. And after that you are going to continue creation 0 or 1, because if you enter 0, that means it stops creating the binary search tree. So if you want to add more number of data into the binary search tree, then you have to give 1. Okay, that is what happens in the case 1. Case 2 is for what? Case 2 is for searching the element in the binary search tree. So for that you have to give the data, that is key data, the element which you want to search. Okay, after that you have to pass that value in the data into the function, find element function, data as well as the root address. Okay, then case 3 is by Inorder traversal. Case 3 is Inorder traversal. So you have to call the function Inorder traversal. You can see here, and with the Inorder traversal is going to take root address. Okay, and similarly Preorder traversal is going to call the function Preorder with the, and as a parameter you have to give a root address. Next, finally post-order traversal. Post-order function I am going to call, okay, and it is going to take what? Root address. Okay, this is what the case, and case 6 will be the exit. You can exit from the menu. Okay, default choice will be your wrong option. So this is what the program, and we'll see the output of the program. Now here we'll understand the 12th program of data structure laboratory. That program I have written under the file name hash.c. So this is the program. Okay, so here let's understand the aim of the program. Given a file of n employee records with a set k of keys which uniquely determine the records in file f. Assume that file f is maintained in memory by a hash table of m memory locations with L as the set of memory addresses to addresses of locations in hash table. Let the keys in K and addresses in L are integers. Our aim is to develop a program in C that uses hash function h dot k gives L as h of k equal to k mod m, and implement a hashing technique to map a given key k to the address space L. Resolve the collision, if any, using linear probing. So before actually implementing this program, let us understand what hash table says. Hash table here, whatever you are going to construct is similar to array. Okay, and the keys are the records you are going to store in the keys. Keys are nothing but the records actually, which you are going to store in the hash table. Like how you store the array elements, the same way you need to store your records in the hash table. Remember, hash table is nothing but a array. Okay, hash table is nothing but a array. What we are using here array for implementation of a hash table. Okay, now I am going to store key k. Okay, I am going to store key k in the hash table. So to store key k, you need to map that key to the addresses of the hash table, So to map key k to the addresses, we need some hash function. That hash function what I am going to use here is a reminder method. You can observe k mod m. I am going to use a reminder method. Okay. So then if in case at any location the collision happens, means what? If any key is already present in that particular location, then you have to resolve that by using a linear probing method. What do you mean by what linear probing method is going to do? It is going to find the next empty locations, okay, in a circular manner. Wherever it first finds the empty location, it is going to place the key over there. So that is what hash table is going to do. Okay. Now let's understand the program one after the other. Hash include stdio.h, stdlib.h. These are the header files I am going to include. Then the maximum locations the hash table is going to take is 10. Okay, and I have here used 3 functions: create, linear probe and display. What's the purpose of it? Create is for creating the addresses for a key. Creating the addresses for a key. That's why I use create function. Then what linear probe is going to do? Linear probing is going to store the key in the this function is going to store the key in the appropriate location. If a collision happens at the particular location, then it is going to map that key to some other next empty location. So that is what linear probe is going to do. Next is about display. Okay, next is about display. Display is going to show you the display of the that is the hash table contents. That's it. So let's understand now main. What main is going to do? First of all, we have declared an array. As I told here, array hash table is implemented in terms of array. So a of maximum size is 10. Then num, key I are the necessary variables that I have declared here. Okay, let's understand. Initially I am going to place -1 in the hash table. What's the meaning of minus in the hash table? That is array. That means it says that hash table is currently empty. Okay, that is why I am using these for loop. So this for loop is used to initialize the hash table with -1. You can observe here all a of 0 -1, I becomes 1, I of 1 also -1, so until max. So all the locations of array or a hash table is filled with -1. Next, what we are going to do in this portion here, every time you enter the data which you want to place in the hash table, and then key is created for the hash table. Key is nothing but a, now here it is nothing but a address. Address you are going to, okay, let me take address. So address I am going to create, I am going to take a address for a key, whatever you have taken. So let me take now this as address and this as key. Okay. For a key, I am going to find the address. So that is done by a create function, and that address I am going to send it to a linear probe function, which will linear probe is if that particular location address is empty, then it is going to place the key in the hash table. Okay, then it's going to place the key in the hash table. Suppose if you want to enter a more number of elements, then you can press 1. So that's why it keeps continuing as answer is initialized with 1. You can observe. Okay, once the key is placed in all the places, and the collision has been that is, if the collision, wherever there was collision, that was really resolved through linear probing, then you can finally you can display the hash table. How do you display that? By calling the display function. Let's understand what create is going to do. You can observe here the create function. Okay, this is a create function here. As soon as you enter a key, okay, what it is going to do? It is going to find the address for a key. It's going to find the location for a key. Okay, it's going to find the location for a key. So here it's going to finally return the address for a key. So this is the change I am going to make. Then so that's what create is going to find the address for a key. Now for the linear probe function, you are going to send the address of the hash table. then the address, corresponding address of the key it is going to send. Okay, suppose A of address, okay, suppose A of address is -1, any location is equal to -1, then you can place the key at that particular address. You can place the key at that particular address. That is what you can do. If suppose the location is empty, then you can place the key in that address. Otherwise what? Suppose if the collision happens at a particular location, then you, as I told, you have to find the next possible empty location. That can be even in a circular, that can be in the circular manner. Whichever that is, you have to find the next possible location. Okay. So now in this while loop, first I am going to check how many number of elements already have been placed in the hash table. That is, what's the necessity of this particular while loop, you might think. So this while loop is necessary to check whether the hash table is full. So that's why I am making use of the count. Suppose the hash table is full. Okay, then you can tell that hash table is full and display the hash table. That is what you can do. Okay, that is what you can do. Suppose the hash table is not full and collision happens at a particular place. See, this else part you are going to enter only if the collision happens at a particular location. Suppose the hash table is full and not full, then what? Then from the, see, you will have the location where the collision happened. So you can check the next possible empty location, that is from the address +1 till max. That is from address 1 till max. Is there any empty locations? Okay, is there any empty locations? So if there is any empty locations, then you can place the key over there. Okay, that is why you are using this. If suppose in those places, that is from address +1 till max, if there is no empty location, then you can use the location. You can start searching the empty locations from 0th position till address -1. Okay, till address -1, that is less than address. Till then you can select, because I have told already you can select the empty locations in the circular manner. So from address +1 till max and from 0 to address -1. So you can search in those locations. So now if suppose address +1 till max, if the location is not empty, then you can go for 0 to address -1. If somewhere the location is empty, then you can place the key in that particular location. That is why we are using this particular while loop. Next, once linear probing is done, this is about the linear probing program. Once linear probing is done, next we can display the hash table. Display the hash table is similar to display the hash table is similar to the array displaying. So from I equal to 0, I less than max, you can go on displaying the contents of the array. Okay, here you are displaying the address as well as the contents of that address. So both you are going to display. So that's about the program. Now we'll see the execution of the program. Let me save whatever the further changes, whatever I have made. So I will compile hash dot c minus o hash dot slash hash. Now enter the data. So this is the heading. Enter the data which I want to enter. The length of the hash table is 10. So first I will enter 23. So do you wish to continue? Yes, I will enter some more data, 42, then 1, then 56, 1. So observe here 23 where it is going to place in the hash table. 23 maximum value is 10, 23 percentage 10, that is 3. So 23 is going to occupy the 23 percentage 10 is 3. So 23 is going to occupy the third location, 0, 1, 2, 3, that is 3, location 3. Okay, it is going to occupy that location, whereas 42 is going to occupy the second location 2, whereas 56 is going to occupy location 6. Now again I will enter data 33. 33 if I press, what happens? 33 percentage 10, 3. At 3 location 3 already one person has taken a place. One person has taken a place. So let me show you. Before actually entering the 33, I will enter some other detail, 44. So let me show you the hash table first. Do you wish to continue now? No. So you can see here the hash table is this cell. This is how it is going to take up location. 42, that is 23 is going to take a place at 3. Okay, that is third location. 42 is going to take second location. 56 is going to take a location 6. Then 44 is going to take a location 4. Okay, now let me run once again and show you. Enter the data. The same data I will enter 23, 1, 42, 42, then 1, 44 and then 1, 56. Now if I enter the data 23, then the collision will happen at the location 3. Collision will happen at the location 3, right? So because 23 is occupied this place. So what happens? It's going to find the next location from 4th empty location, next empty location from 4th to 9. Suppose if there is no location at from here to here, then it is going to find the location from this place to this, that is 0 to 2. That is what it is going to do. Okay, from 0 to 2, this particular location. If suppose if there is no location at these place after this, then it is going to take a location from next empty location from 0 to 2. So now I will enter and show you how it is going to. Suppose if I enter 33 this time, enter the data, no, 0. Do you wish to continue? No, 0. Sorry. I will place one more, 66. Enter the data. Do you wish to continue? No, 1. It's sorry. I will enter 66 this time. So it is collision detected, collision avoided successfully by linear probing. That is, I here entered 0, 0 would have occupied at this place. So when I pressed 66, it was supposed to take a location at 6, but 56 was already there. You can observe here 56 is already occupied the 6th location. So where 76 is going to take place, that is at next empty location after this. Next empty location after this is 7. Suppose here if there is no location present, that is empty, then it is going to select from check from 0 to 5. So that is what it is going to do. But here at 7 it is empty, because how did I come to know that 7th location is empty? That's it's equal to -1. So do you wish to continue? No, I want to see the hash table. So you can see here 66 has taken this next empty location. So this is how you can actually solve the hash table.